Thank you all for being here. Today we will be presenting on the Diagnostic Survival Diseases Project. My name is Brittany Shirk. I'm a senior electrical engineering major.
My name is John Cison. I'm a senior biomedical engineering major.
My name is Michael Geyer. I'm a senior computer engineering major.
To get us started, I'll show a quick introductory video explaining our project. Our team was founded on the principle that patients in the developing world should have access to accurate information concerning their own health that is based on sound medical research in order to receive timely treatment. Specifically, our project is focused on HIV diagnostics, and we are partnering with the Matcha Research Center in Matcha, Zambia, which serves over 5,000 HIV-positive individuals.
In 2015, our team came about due to recognizing a strong need for a better point-of-care diagnostic tool for HIV, especially in low-resource communities. A child diagnosed with HIV at the age of 2 will need a minimum of 120 viral load tests in their lifetime to properly monitor a viral infection. Our team is coming alongside the Matcha Research Center to serve the community with a point-of-care diagnostic tool.
Our design criteria for this tool includes that it must be a quantitative viral load count so that treatment is able to be monitored. Quantitative tests are less accessible and more expensive than qualitative tests, but they are important because the concentration of viruses affects the treatment path. With that in mind, our goal low-end threshold is 1,000 viruses per milliliter, which is a low concentration, and to be able to distinguish concentrations anywhere above that.
Other considerations are that we want rapid point-of-care results, which means we want it to be portable, and we want to reach a lower cost, which for us looks like a goal of less than $10 per test and a device cost of less than $5,000. To give an idea of scope, these devices can cost upwards of $20,000. We also want this to be usable in different types of communities and with varied levels of training, so we want to have an easy-to-use interface and simple test method.
For our design methodology, we developed a fluorescent probe that binds to GP120, a protein found on the surface of HIV in a patient's blood sample. We then shine a laser at the sample, causing the protein probe to emit light. This light is picked up by a detector which converts the light signal to an electronic signal. The signal goes to a field programmable gate array, or FPGA, which uses an autocorrelation function to relate the electronic signal to the concentration of HIV in the sample. Summary results from the autocorrelation are then interpreted and displayed on a user interface.
We would like to thank all previous and current project members, mentors, and partners for their contributions.
So to detect HIV in a viral blood sample, we use a fluorescent probe that binds to the protein that's on the surface of an HIV particle. Our optic system is able to then detect this fluorescent probe. To do this, our optic system uses a method called fluorescence correlation spectroscopy. First, we shine an excitation laser at the fluorescent probe, and the fluorescent probes, when they're excited, will emit an emission wavelength that is picked up by our detector. Then those photon signals are autocorrelated to determine a viral load diagnosis. Now, the issue is, how do we determine the difference between an unbound fluorescent probe and a fluorescently labeled virus? One of the methods we have previously explored is, in addition to our FCS channel, we also use a light scanning channel that tells us the size of a particle passing through the focal body. That allows us to tell the difference between a small unbound fluorescent probe and a larger fluorescent probe bound to a viral sample. But currently, we use a method called autocorrelation. In this method, we determine it's more efficient because we only need the fluorescence channel. And by using this FCS data, we run it through an autocorrelation algorithm that tells us whether a fluorescence data is a significant viral event or just an unbound fluorescent probe. To be able to conduct this testing, we need to calibrate our optic system. A fully calibrated optic system will have a laser power of at least 50 microwatts to be able to conduct any reasonable test. To make sure that we reach this threshold, we use a power meter to evaluate the power output of the laser at all points in the system. We have recently reached this threshold and gone above it, but let me tell you about how we got to that point. So with calibration of the optic system, we have 4 areas in the optic system that need to be correctly calibrated or aligned. In these 4 areas, there's a total of 15 screws or adjustment knobs that need to be reasonably calibrated to get a functional optic system. In order to do this, we created a standardized procedure that allows someone without former background knowledge to be able to come up to the optic system and learn how to successfully calibrate the full optic system. To do this, we use a lot of engineering principles to be able to isolate individual components of the optic system and calibrate them one stage at a time. In addition to that, we created these fixtures that minimize the variability from person to person and better standardize that calibration process. With a fully functional optic system, we can then conduct something we call end-to-end testing. That includes preparing the viral sample, then putting it in the optic system and running the tests, and extracting that autocorrelation function data for later plotting. With this, we can determine things like the correlation of a virus in a tested sample, so the concentration of virus in the tested sample. We can create a relationship between that and how many viral events or fluorescent events there are per minute. But the most important thing is the data we're getting out of this end-to-end testing for further research. So one way we can look at these test data is by the manual interpretation by graphing the SCS data of how much fluorescence is being detected over time of the test. More importantly, we can also autocorrelate the data of these tests. Using a program developed by a previous project manager, Dr. Matthew Fair, we run an autocorrelation algorithm that outputs data that can then be post-processed into a graph that a clinical specialist can look at and determine a viral load diagnosis, so they can determine if it's HIV positive blood or not. But in all scope of this, the optic system trials are done with expensive lab equipment, and this is not good for a low-cost device. So as we are determining and validating the feasibility of this process, we then incorporate it into more affordable materials for a low-cost device. I'll now hand it off to Brittany to talk about the incorporation of those parts.
So now we'll be looking at what we call the photon processing section of our system. So this is the part that takes the light that is emitted by the probe and converts it into an electrical signal for signal processing. To do this, we use a device called a silicon photomultiplier, or a SIPM. The SIPM is a tiny little chip that detects a photon and emits an electrical pulse for it. However, the pulses that come out of the SIPM itself are very small magnitude, around the order of about 10 nanovolts. So in order to actually be able to do some processing on that, we need to convert that to something more like what you see on the right here that is boosted in voltage and is also a digital signal rather than an analog one. Our system for doing this is using commercially purchased printed circuit boards that are at a much cheaper cost than the lab grade detectors that John is currently using for his testing. This involved an evaluation board that has the SIPM itself mounted on it, along with 2 amplifying units to boost the voltage up and a final discriminator to convert from analog to digital. Some of my work has been focused on confirming the operation of each of these individual boards. Starting with the amplifier itself, I wanted to look at the range of frequencies within that we get the optimal gain out of the amplifiers. So I used a function generator at various input frequencies and measured the gain at the output. You can see here that the amplifier gets optimal gain at a range of around 50 kilohertz and above. This works well for our system since the SIPM we use is known to have a dark count rate of about 53 kilohertz. So we'd be expecting to work in the range of 53 kilohertz and above when we expose it to light. From here, then we want to confirm that the amplifiers also operate well with the discriminator. To do so, I used a function generator input at a small amplitude of about 4 millivolts peak to peak at around 53 kilohertz as our dark count SIPM rate. I input that to both of the amplifiers and through the discriminator, and then put that output on an oscilloscope to analyze it. That output looks like what we show here. So in blue, you see the input signal that is coming from the function generator at that 4 millivolts peak to peak value. It then goes through the amplifiers and the discriminator, and the yellow is what we get at the output. So you see here, the voltage has been boosted to about 2.5 volts peak to peak, and it's also a square wave digital signal. And the frequency matches that of the input. There is a little bit of a phase shift here, but we're not too concerned about that because we're more concerned with the frequency at which we're seeing pulses rather than when exactly in time they're occurring. Then from here, we had to finally add in the last part, which is the SIPM itself, and see what happens when we put that as the input to the amplifiers, and then through the discriminator. And what we get on the output is something like what you see here, pulses that are boosted up. Here it's about 2 volts peak to peak, so it's boosted up, and it's also at that square wave shape, so it's a digital signal. We also know that it was tested, the SIPM itself was tested in darkness, and we're getting an output rate of around 53 kilohertz, which makes us confident that the system is getting all the pulses that is coming through the system. To talk then about what we do with this signal to get a diagnosis, I'll pass it off to Michael.
Thanks. Now that John and Brittany have gone a bit more into their individual sections of the project, I'd just like to take a second to reiterate what the overall project flow looks like, the data flow. So from the optics section, which is John's part, we'll send a light signal to the photon processor that will convert that light signal into an electrical signal that can then be sent to the FPGA, which runs an autocorrelation function on it. Then the FPGA is responsible for sending that data to the Raspberry Pi. I'll touch a bit about how we do that in a second. After it's sent to the Raspberry Pi, it runs additional data processing and sends that to a graphical user interface or a GUI, where the end user can interpret those results to determine the viral load count. From there, they'll be able to determine a treatment path. So to begin with, I'd just like to emphasize, actually, one more thing I'd like to note. In using the Raspberry Pi here, we hope to replace kind of more expensive equipment that we would ordinarily have to use. Ordinarily, you could hook an FPGA up to a computer, and through various forms of software, you could accomplish the same functionality that we are hoping to emulate via the combination of the FPGA and the Raspberry Pi used here. Now, I want to emphasize that the Raspberry Pi is largely in control of the data flow. So after the FPGA receives the electrical signal from the photon processor, it will convert that from electrical to a digital signal that can be sent to the Raspberry Pi. The issue being, how are we going to communicate that data between these two devices? Also, we have 64 bits of data that we're trying to work with, and the FPGA that we're working with is only capable of sending 8 bits at a time. So that creates another issue. I'll talk a bit more about that in a second, but just know that after it receives that data from the FPGA, it can then send it to the GUI, as I mentioned. So how are we going to communicate between these two devices? Well, we work to establish a form of serial peripheral interface, or SPI. In this, there is a primary device and a secondary device. Here, the Raspberry Pi will act as the primary device, as it can send commands to the FPGA, but the FPGA cannot send commands to the Raspberry Pi. The FPGA can only send data to the Raspberry Pi. So I have a list of commands present as examples of what the Raspberry Pi could send to the FPGA. For instance, it will send things like, send me data, are you finished with your autocorrelation function or not? So in the scope of our project, it will first ask the FPGA, are you finished with your data processing or your autocorrelation function? It will wait until the FPGA sends data back that corresponds to a yes. The Raspberry Pi can then execute a program that will send us a series of commands telling the FPGA to send me data over and over and over again until we have the 64-bit data point that we want to work with. Because the FPGA is going to send those 8 bytes at a time until we have the full 64-bit data point that we want to work with. So the Raspberry Pi is responsible for directing the communication between those devices and reconstructing the data once we receive it. After that, as I mentioned, it has to run further data processing on it. This data processing was largely handled by previous team members and has already been established. A skeletal figure for the GUI has also been established, but there have been some modifications to it. Actually, we've created 2 alternate versions of it, one of which makes it easier for testing. We're able to execute individual sections of the program at a time to make it easier for testing. Another version is to streamline the process as much as possible for an end user. So all they'll have to do is press a single button. It'll take care of the entire process and send the results to them. So in summary, the optics system, John's part, has a standardized procedure to prepare and test samples using fluorescence correlation spectroscopy. That's then sent over to the photon processor, which circuitry can detect the light pulses and convert them to a digital electrical signal for processing. That gets sent to the FPGA, which runs its autocorrelation function on it. And then we establish the communication between the 2 devices so that they can transmit the data and recombine it for signal processing. And now I'd like to open it up to any questions.
Where do you stand on your communications between the Raspberry Pi and the FPGA? Is that complete now?
Yeah, I'm glad you asked about that. So is the communication between the Raspberry Pi and the FPGA complete? Kind of. We sent a batch of test data between the 2 devices, and it was able to accurately receive the data we were expecting in a small test batch. But whenever we try to simulate, we actually hooked up a PIC processor, which is going to emulate the Brittany's role with the photon processor. That's sent to the FPGA, and then it tried to send that to the Raspberry Pi. We were getting it to establish the communications and send the data back and forth, but we weren't getting accurate data, or at least the data that we were expecting from that. So there is still some work to be done there.
The chemistry on this, you tend to get a good correlation between positives and negatives, and you tend to get false positives, false negatives.
That's a good question. So the question is, how is our ratio of false positives to false negatives? true positives, true negatives. So we've conducted our like specificity sensitivity calibration in the past, and we've been able to reach a point where we can comfortably say that it will detect if there's HIV positive in a blood sample or viral positive in a blood sample. We just can't like provide the reliability currently of the concentration, but for positivity and negativity, yes, we think we're at a good spot.
Questions? So for the output of the silicon photomultiplier, in the past, there was an issue with, I think, an impedance mismatch between the FPGA and the output of the discriminator. Was that something you were able to solve?
I didn't figure out what the problem was. All I know is I don't have that problem anymore. When we try to put it as an input to the autocorrelation though, we're not getting things out that we would expect to based on what we're getting from the lab grade system. So there's still some work that can be done to figure out why there are differences with that, but I have not been experiencing issues with impedance mismatch where it was like ringing back like it had in the past.
Can you briefly explain can you briefly explain the autocorrelator algorithm? Like what were you correlating? It's the number of photons, like you mentioned like the dark rate of, I guess those are false, right? That's not actually HIV. So are you correlating that number? And like what exactly is that process?
Good question. Asking how the autocorrelation function works. So yeah, the dark count of the SIPM is basically pulses that will output even with no light input. It's more based on thermal energy. So there will be pulses out of that. So the algorithm should be able to correlate, like I would assume it. I don't know completely detailed. Actually, Dr. Ferrer is the one who wrote our algorithm currently, but it would take into consideration, I believe, the dark count and look at how much greater the rate is than that, and be able to correlate that to a diagnosis and a concentration of HIV.
I noticed there are two different amplifiers in the circuit. Is there a reason why, first of all, there's two, and second of all, why they're different? Sorry, they look different. I don't know if they actually were different, but they did appear.
So they're two amplifiers, and then this discriminator was something separate actually. So that was a different board. That's what makes it the square wave. But the amplifiers themselves, we have two because we need two to get it actually to a voltage level that we can work with. So that's the reasoning with that, because they're commercially purchased ones. So we found them online and purchased them, and we decided we needed two of those modules in order to actually boost it up enough. And we'll be out in the lobby then if there are any further questions. Thank you all for being here today.